that lowers the probability of, let's say, a random guess about the question. Okay? See, the problem, let's say, if you think back to that Wagner-Mike-Yarick, is it's very easy. It's a 50% chance. Okay? If you did it 10 times, the probability of the answer 10 times is 1/2 to the 10th. That's a little way less than a half, so you could do that. But, all right. Now, how do we actually do this? What kinds of questions can we ask? So the protocols then, oh, remember I said it's two-way authentication. I forgot this. If you do it, the same thing works the other way. You could submit, the bank has your word, your group too, stored. So it verifies the verifier to the prover also. All right. Now, here's the basis. This is a free subgroup method. And this is why I said about free group cryptography. And this is really the simple idea, but that it really works. So what we're going to do, we'll assume that both the prover and the verifier has a group randomizer, each per password. Now, the challenge group in this case is a subgroup of the free group. And we give the subgroup by giving a random set of words in our original generators. So the password is linked to a set of words, W1 up to WK. And K is not equal to N. K is random, N is random. Okay, with me on that? Mm-hmm. Now, the prover has the group stored on their machine. The verifier has the group stored on their machine. Now the prover submits the standard password. Now what the verifier submits back as a question is a random free group word on Y1 up to YK. Okay? Now the prover is not doing this by hand. It's all machine to machine, which takes a lot of the pressure off. The prover then treats that word as a word in their generators, W1 up to WK. So they're evaluating that free group word in a subgroup. But that random free group word now is a giant word in the original X's. Has cancellation and so on. So what we do is the prover then rewrites it, does all the cancellation, sends it back as a word, not in the Y's, but a word in the X's. The verifier checks if those are equal in the original free group. If they are, that question has been answered successfully. If it hasn't, then access is denied. Now there's a very little chance, like in the standard, that you spelled it wrong or whatever. So one miss, you're out. There's no, are you sure about that answer? Now it does it a finite number of times. Now there's one proviso. This is to prevent middleman attacks and all of that, is you never submit the same word as a challenge word. The machine stores the record, and this isn't a big storage problem on a computer, stores the questions that are asked. So it has the questions that were asked. If a question is asked, and a question meaning a free group word, that's already been asked, it's denied. The prover then stops. And if it goes the other way, the prover stops, the verifier stops. Okay, with me on that? All right, now, to verify that it's legitimate, the process is repeated. Very, very simple idea. I'm going to give you a security proof of this in a moment. But before we do that, if you take a look, the attacker has access only to the transmitted words. Given a series of free group words, and this is where the strong generic free group are, there's a probability of 0 of reconstructing the subgroup. But we don't want to attack to use an already signed word. That's now the beauty of the system is that change is extremely easy. Change one or two of the words. You know, let's say we'll use the bank example again. The bank says, look, your subgroup has been attacked. We are planning on changing the following words, and maybe there's a a secret way of changing it, or you have to come into the bank, something like that. Unfortunately, you can't get away, and all the backup password systems have to have this. There has to be an initial face-to-face. You know, even in time.rsa, you have to have a device that's specific to you. I told you, my daughter has this thing at Ernst & Young. It's random, but you have to have already been signed in on your password, and then they send it directly. So in her case, for somebody to get in, they have to steal her device as well as the thing. So,
but they can intercept the communication.
What?
They can intercept the communication with the device, no?
Yeah.
I mean,
yes, someone can.
If it's being sent wirelessly through,
oh,
let's
yeah.
say,
No, you can.
some wireless network,
you can.
it might not be a local. I mean, it would have to be local. But if you're in a library,
that goes with the middleman attack. If somebody intercepts the, so you want to do that. All right, now, essentially this presents a one-time keypad, and there's an enhancement. I won't mention that now. The general finitely presented method does exactly the same thing, exactly the same, but instead of using a set of free group words, you have a finitely presented group. You do the same thing. They give you a word in the finitely presented group, okay, a random free group word, and you rewrite it in the normal form of your particular group and send it back, and that's what's checked. In that case, you have to assume in group theory language that essentially the group you give out is automatic. However, there are infinitely many choices for challenge groups. All right, now, what is the security of this thing? Okay? Now, we'll assume that the adversary has access to the transmissions. Why is that not a problem? Well, each time through, you're submitting old stuff. If the adversary steals something, that something in this session is never going to be used again. So it kills the middleman attack. Knowing the answers to that particular question is worthless. So essentially, there are two theoretical attacks. I'm going to do those. But it's essentially, they ask you infinitely many questions. What's your mother's maiden name? What's the number of red blood cells you have? And there's an infinite number of questions. But there's an infinite number of questions that are listed nowhere except in the group. And if there's a problem, they can change it. And if a question has already been asked, they won't ask it again. Now, there are two theoretical attacks that I have to address. The first, where did I go? I'm going the wrong way. Aha. So the most straightforward attack is for an adversary to collect enough challenge words and answers. But what is a challenge word? Remember, you're sending out questions. Let's think of this as the free group case. You're sending out words in the Y's, and you're sending back words in the X's. Okay, do you follow me? Mm-hmm. Well, let's say the attacker steals that. What does it give him? It gives him an equation in a free group. W of this expression in the Y's equals this expression in the X's. And let's say he collects a whole bunch of them, 200 of them. What does he have, he or she? They have a system of equations in a free group. Okay, now how do you solve a system? Of course, there's all this stuff, McCann-Rasparoff and all this stuff, which is incredibly hard. In fact, it's provably hard. There's a result of Lishanuk that solving any system of equations in a free group is NP hard. So that means that solving this system of equations is theoretically infeasible. And we'll give some enhancements to make it even harder to solve, but it's NP hard. So for them to collect enough and then just solve is just infeasible. They can't do it. Now the second one was pointed out You see, as you collect these, you're getting a homomorphism. Yi goes to Wi. Now,
Yes, I have a question. Is that result a generic case or just a simple basic complexity?
just basic, Lishonik's thing is just basic complexity. I'm going to get to the why we need the generic over here. You see, Yi goes to Wi is a homomorphism. Well, maybe if you collect enough responses, your new word is a combination of your old words, and you can answer the question without actually finding the group. Do you follow what I mean? Because your new is a combination of the Y's, you know the homomorphism. And here's where the generic thing comes out. It turns out each set of challenge words is a free basis for a subgroup they generate. This is something called the strong generic free group property. So if you get one homomorphism, it doesn't give you any information about any more homomorphisms. So the thing is theoretically secure in that sense. So that's the system. Let me just say one thing about several enhancements. You can throw in a noise thing. One thing is short challenge words. The words you send out should be short, because that gives you need many more equations to solve. So let's say that you have 200 possible variables. You have a free group on 200 generators. Your challenge words might be words on 5 generators. Because then the next message you send out, which presumably they're trying to sell your words, will involve 5 different W's, and they won't do it. So use short words. You also have to pick words, and this is this can be done. Oh, a frequent reset. But you should pick your words W to have much cancellation. And the way you do this, and I won't get into the theory here, is to sort of reverse Nielsen transformations. Nielsen transformations are a method in free groups to take a complicated group, chop it down into its simplest form. But using reverse Nielsen transformations, you take a word and you chop it not up, you build it up to get words that have a lot of cancellation. That way it makes the solutions harder. Now, final thing, and I'll stop. Was I supposed to be done already?
No.
You know I can talk forever. Because drugs. No, don't wait for that. Okay, now, part of the proof of the security depends on what's called a strong generic free group property. There should be an R in property. Not the way I say it, but there should be an R in property. I don't say the R. See the word there, property? All right, asymptotic density. Now, asymptotic density, if you haven't come across it, is a method to compute densities of probabilities of infinite discrete sets where you want to consider the elements equally likely. Now, asymptotic density originally came from the idea of, if I asked you, if you randomly pick an integer or a natural number, what's the probability that it's even? Well, you'd like to say, what?
102 is like what?
You'd like to say that it's 1/2.
Yeah.
But how do you make that precise? Because the integers, they're all equally likely, but the whole sample space is infinite, and the even numbers are infinite. How do you make it precise? Well, I don't know who did it originally. I think it was Percy Diaconis, but I'm not certain. But essentially what they said is, look at n integers. Now, what's the probability that if you're given, let's say, 1 to n, that the thing is even? Well, it's either 1/2 or 1/2 plus 1 over n plus 1. If you take then the limit as n goes to infinity, it's going to be 1/2. And that's called the asymptotic density. Make some sense?